So our first presentation is going to be on IoT design, past, present, and future. For that, we are turning to David Loadman, who is president and CEO of Konrad Technologies North America. He joined the company last year. He was previously at National Instruments, and when he was at NI, he worked with wireless sensor R&D, as well as their wireless test. So David,
it's all yours.
Enlighten us.
Where is that? Yes. Okay. Can you guys hear me?
Just make sure you speak straight into the mic.
Okay. All right. Well, good afternoon. And a lesson learned here, don't be the first meeting right after lunch. So I'm going to talk a little bit about a recipe for success. What I was asked to talk about was kind of paint a picture of a problem in the IoT space and map it to how things were, how they are today, and then where are some of the problems and challenges that are going forward. So what I'm going to use as a proxy is autonomous driving. So whether it's ADAS with assisted or AD with autonomous, either one of them is applicable in this discussion. And specifically what I'm going to talk to is the challenge as it relates to the physical sensors that collect the data. And as I listened to the earlier sessions, there was a fair amount of talking about the sensors and the data, but it was mostly targeted at that data going back into the cloud or back into some remote location where it's monetized or worked on. This is going to be a little closer in. This is going to be the data that's actually being worked on and evaluated within on-premise, if you will, in this case in the vehicle. Specifically, what I'm going to talk to are just three of the sensors, radar, LiDAR, and camera, but you could map this to medical devices, you can map this to consumer devices. I think the same challenges, scenarios will apply. So if I look at the legacy, the other thing I'll ask you is a little bit of leeway here. So I'm going to speak in pretty broad generalizations. I'm quite certain that some of the examples I give, there are people that are doing things much better than what I say, and there may be people who are doing things that are even less than what I'm talking about. And if I break things into, typically in my world, we look at two things. We look at how do I validate something from a design perspective that I know that the design is proper and is going to work according to spec. And then secondly, how can I build that design in a scalable volume, in a high volume? I can do it repeatable, and I can do it with quality, and I can do it with minimal cost. So if I look at these sensors as it relates to the automotive industry, by and large, these sensors have all been tested in isolation. If you look at the backup camera, you look at the radar that might be being used today for blind spot detection or possibly assisted cruise control, these sensors and the functions that they're testing are strictly being tested just within the context of that one function. Right? It's typically not being tested with other sensors and how they interoperate. The other thing that I've noticed is as you progress in the supply chain from the silicon up to the module to the subassembly to the vehicle, the level of testing that goes on as you get further and further out to the finished product becomes less and less and less. And when you get into subassemblies and actual vehicles, what you actually end up getting are very, very simple go-no-go testing, sometimes maybe even a fixed target or just a golden device that they can reference against it. And when you come to the validation, everything is for the most part, almost everything is relied on drive testing, right? So as you look at what's going on now with autonomous driving or assisted driving, and I've been kind of going back and forth between San Jose and Detroit, and these two centers, which have vastly different cultures, I think everyone's aware of. But the one thing that's consistent, the one message I've heard again and again and again, which is there is no way that you could just rely on drive testing. It's too expensive, it takes too long, and they have to shift the testing further left, especially a lot of these algorithms. They can't wait till they actually can build a car to test how all these algorithms and all these sensors work together. So in order to be able to do that, the challenge is to be able to test these sensors both more explicitly in a lot more corner cases in terms of environmental conditions, and be able to do it in a lab, and to be able to do it in a manner that actually faithfully replicates the real-world environment they're going to end up in. So again, I don't think there's anything here that's unique to automobiles. You could apply this to medical or other devices. So if I just quickly, just very, very simple, again, I'm not going to get anywhere close to any of the specific level of detail. If you look at radar, the one thing about radar, it's kind of similar to what's going on Wi-Fi. What the radar industry is going through now. Up to now, the radar sensors have been working at 24 gigahertz, relatively low bandwidth. Now with the sensors that are coming out for autonomous driving, you're now in the high 70 gigahertz bandwidth, or gigahertz frequency range. You're in bandwidths that are 1 gigabit per second going to 4. The equipment that's required to test this is all new. Most of what's being used right now is relatively slow and cumbersome. And then the ability to actually create a scenario, right, to create and emulate a target for a radar without actually having to go out and take it on the road is a challenge that right now is being solved by many, many people in the industry. But to be able to faithfully recreate a target, and then not just a target, but actually a complex scenario of movement, and then multiple scenarios of targets that are moving at one time, is becoming one of the bigger challenges that are taking place in the valuation of radar sensors. Now, LiDAR is interesting to me because LiDAR, the challenge of LiDAR is that this is a technology that's coming out of the mil aerospace industry. And by and large, it's been a relatively low volume technology. For the most part, a lot of these things are hand assembled, hand tested. The assembly and manufacturing processes are targeted at tens, hundreds, maybe thousands, but by no means millions. So if you look at the whole challenge that this industry, this supply chain as a whole has, not only do they have to figure out how to do better methods to test and to be able to subject the LiDAR sensors to different real-world scenarios, they also have to figure out how to scale the manufacturing process, which is a double challenge for these guys. So this is again, and I think this is just a proxy for a lot of other things that are going on with IoT. You're getting a lot of these technologies that were being used as early adopters with relatively low volume, and then immediately they end up getting into these very large-scale deployments with actually no process in place to be able to scale. The last one is cameras. Now, cameras is interesting because on the surface you would look at this and say, well, that's the most mature technology, and it is. The challenge with camera testing that I like to use is if I walk into any automotive OEM or I look at anybody who's doing autonomous driving projects, and you ask them how they're testing their camera algorithms. And they'll take you into a room, and that room's got an actual vehicle in it, and that room's typically got a geodesic dome that's got a VR projection of a 360-degree view of the objects that it's seeing in its real world, in its simulated environment, or it's got this bank of large screen expensive monitors. So what doesn't exist right now, by and large, is the ability to actually project images onto these sensors and do it in a lab environment, and do it in a manner where I can either bypass the actual CMOS sensor itself and go directly into the digital interface, or actually test out the sensor as well. And then in addition, if I want to do things like I want to add a blur effect because I want to simulate rain and fog, or I want to change my lighting conditions, many of the conditions you see in laboratories don't lend themselves to being able to do that quickly and easily. So if I look at the grand challenges coming up for autonomous driving, the one thing I'll do is just level set. And a lot of people use this word sensor fusion or this phrase, so I don't want to specifically say that this is the right definition, but this is the definition that I want to use to speak to the frame of reference that I'd like to put in place, and that is that I really look at sensor fusion as really, it's a process where by taking an aggregate of data from multiple sources, the level of uncertainty I have in making a decision based on that data, that uncertainty is smaller than if I only got data from one source. Seems like it makes sense, it's pretty common sense. But here's the real detail. So what many, many people that I talk to want to do in the automotive industry is literally, they want to lay the vehicle out in a lab on a table. They want to take all the sensors, they want to take all the ECUs, all the buses, and they want to be able to be in a lab environment and test their algorithm, their model, if you will, for the car. How that model is going to respond to sense the changes that it sees in the conditions as indicated by the sensors. So The challenge is twofold. One is, do you have an accurate model for the car? And there are many people doing that. And then there is this concept of hardware in a loop. And if you're familiar with that technique, but basically it allows you to take your algorithms and then actually have those software algorithms interact with real-world devices like a motor engine ECU, or the seatbelt safety system, or the headlights, et cetera, the blinkers. Now you take that model, and that model is actually telling you, in terms of your simulation, where am I on the road, and what objects do I see? And that should inform then a class of target generators. And those target generators are a class of instrumentation, if you will, electronics, that will then generate targets that the physical sensors see as if they were out on the real road. So in the case of radar, it's a radar target. And a camera, it's a visual image, and LiDAR, it's an optical signal. And here's so the challenge now is, how do you put in place a simulation system that works in real time, that gives you update rates, that approaches that which is required to be able to provide driver safety if you're looking at level 4 or level 5 on the road. And then the other item that people are struggling with is, what is the amount of jitter? So in this car model, when my camera sees a bicycle crossing the road and my LiDAR sees a bicycle crossing the road, do they actually provide that data back to the main model at exactly the same time? And the challenge is, any algorithms, how much jitter can you tolerate? And at this point, I don't think a lot of people know, right? They have ideas, but it hasn't been stress tested. And the challenge for the simulation environment is, can you control down to the nano or microsecond that you can guarantee that the generation of your targets that are being presented to these sensors are being projected at exactly the same time? And then can your entire system in a closed loop feedback run at a millisecond or better update rate? So that once you get all that working, then you can test the model, and you can do that before you ever drive. And one of the best requests I got from just a visit last week, the customer said, look, my goal is, if you could come in here, give me this lab environment, and I can go and program my car to go take a drive to 7-Eleven and get a Slurpee and drive back home, then I feel like I've made success. Then I'm able to augment my drive testing with my lab simulation. So as a approach to success, and there's many, but I'm a big believer in this concept of a platform-based approach, right? And the idea that is, and I've heard discussions earlier today, everything revolves around industry standards, right? Everything is around a specific set of standards and specifications that are interoperable, right? And that people know how to work and exchange data between, whether it's a physical interface or a data interface. And then you have a platform of hardware elements that you can use depending on the form factor you want. Do you want to actually put it in the trunk of the car? Do you want to be able to put it in a lab? Do you have to be able to put it in a shake and vibration table, or in a temperature chamber? And then you take all of that, and then you work with domain experts who have specific solutions in IP that, when put together, can solve your problem. So I'll give you an example from our end. This is based upon, if we look at the standards that are in place for this, so the CAN bus, now with deterministic Ethernet with 802.1 AES, many people in the automotive industry are looking at that as a next generation bus that you can use for timing and synchronization. PXI in Windows is some of the enabling components. And then one thing I didn't talk about was V2X. So what about vehicle to vehicle, vehicle to infrastructure? And the funny thing is, when I ask people about that previous slide about sensor fusion, how do you actually add in vehicle to vehicle and vehicle to infrastructure? For the most part, I typically get blank faces at this point. Trying to add that layer of data into the model in addition to these sensors is just a whole nother layer of complexity that also has to be built into the simulation environment. And then lastly is adding domain experts. So one of the things that we've done, that we just formed a collaboration last week, is we created basically it's called 8S IIT, and it's basically a test bed that its goal in life, apologize, I'm going to just, is to actually put this in an actual lab, get it running in real life, and work with automotive ODMs and sensor providers and the car model providers and the algorithm people, and to find out where the algorithms break, where the bottlenecks and constraints are, and be able to do all this before you get the vehicle on the road. So to me, that's the, I guess, the future state of where IoT testing needs to be. It's taking all of your sensors, all of your data, having them all work together in real time and being able to faithfully execute that without having it be in an actual environment, so that you can push that as far left as you possibly can. That's it. Yeah, if there's any questions.
Questions from anybody? You did such an unbelievable job. Everybody has learned. Thank you so much. Give them a hand.